we've okay. So today's lecture is going to be on data structures. We'll be covering what data structures are, the importance of data structures, and then how our choice of data structures affects our runtime. Before we do that, I will do a review of our first lecture. I'll go through a couple of examples and demonstrate basically what we learned in the first lecture and why it's important and how that will apply today. Just one note before we get into that. Today's lecture is covering data structures, sorting, and searching. With this lecture covered, everyone should be able to start on assignment 1, which is going to be due on Sunday. So after today, feel free to start working towards assignment 1. On Friday and Saturday, we will have work periods where you can also get help from the learning support staff. And before and after lecture, we also have office hours. The last thing I'll just mention really quickly is the assignment is due on Sunday, and then the next assignment, assignment 2, you can get started on that after the Tuesday session. So that on Tuesday, we will be covering recursive data structures. With that material, you should be able to complete assignment 2. Make sure you submit on Sunday because we also need to do pairings for assignment 2. Everyone will have partners and you'll need to review the code of your partner. So in order to make sure that everyone has a partner by the time we've covered our fourth lecture, please make sure you submit on time so that we can do the pairings. Okay, let's get started with the material. So yesterday we covered time complexity. That was the main thing that we talked about. And time complexity refers to not how long a program takes, but how the time scales with the size of the input. So the fact that something takes 20 milliseconds or 50 milliseconds doesn't really affect us that much. But what does affect us is whether the runtime will increase linearly or exponentially compared to when we increase the input size. So typically a very common use case is that you're developing an algorithm that you want to run on a big data set, but you can't run, when you're developing the algorithm, you can't keep running on the full data set because that would take too long. So typically what you do is you take a subset of your data. For example, if my data is called my data, I just take the first 100 elements of my data and I feed that into my algorithm. And using this data, I'll keep developing my algorithm until it works correctly. And maybe when I'm developing this algorithm, it only takes 20 milliseconds to run. But when I then run my algorithm on my full data set, what the runtime that I experience then is what really matters to me. If I implement my algorithm efficiently, I might see a runtime of 400 milliseconds, which is completely reasonable. But if I see something closer to like 4 hours or 5 hours, that's something that might be fine, it might not be fine, depending on how long you're willing to wait. So the runtime is basically what determines how this algorithm will scale based off of our runtime, or based off of the size of our data. So we can actually see this scaling in different algorithms. So the first algorithm I have here is, okay, so I'm jumping a bit ahead, but the way that we'll be evaluating our different algorithms is we'll have 3 different lists, one of size 10, one of size 100, and one of size 10,000. So the medium size list is square of the first size, small size, and the big list is square of the medium list size. So 100 squared is 10,000. And I'm randomly shuffling these lists as well. And if we look at this first function, actually I will just clear my output. Actually, it's fine. Okay. So this is my first function. All it does is return the first element of my list. And so I run my function on the small list, on the medium list, and on the big list, and then I see how long it takes to run the function. So does anyone want to guess what the runtime of this function is? And what that would mean in terms of the runtime, the times that we see in the timing function. So what is the runtime, and then how will that affect the output of our timing? Okay, so I'm seeing some responses that's O1. And what does that mean for our actual numbers, like what A, B, and C will be? Yeah, so we should see something that's roughly the same time, regardless of whether it's a small list, medium list, or a big list. So if you actually look at our run times, the amount of time it took to run the small list was 0.00, and there's 4 zeros followed by a 9, and it's the same for the medium list and the big list. And here we can even see, I'm just dividing the two numbers to see what the ratio is. So it is very close to 1. So regardless of the size of the list, getting the first element is the time it takes to get the first element is constant. So it's O of 1. This is our second function. And what this does is it adds the first 10 elements of our list and returns the total. So what is the runtime for this function? And again, I'm running it on all 3 lists and seeing what the time is, the amount of time it takes. Exactly. So even though we're doing 10 steps here, the number of steps isn't contingent on the number of elements in the list. So again, we should see O of 1 time. Now compared to the previous previous example, we might see a longer absolute number. So rather than 0.000096, we might see something that's slightly larger because we have 10 steps. But in terms of the growth, as we increase the size of the list, the runtime should still stay the same. So if we scroll down, that's roughly what we see. So the absolute numbers are slightly bigger, maybe 1 times or 2 times bigger, but the relative runtime between the 3 lists is still the same. We do see slight variations, but that's just random variations in execution. Okay, moving on to the next example. This gets the sum of a list. So it will add all the elements in the list and return the total value. So what would the runtime of this function be? And what should we observe in the values of A, B, and C? Yeah. So the responses I'm seeing are that it will be O of n runtime, and the largest value should be C, followed by B, followed by A. And I think I saw someone say that it will be roughly 1x, 2x, and 4x, because that's we'll see. So let's run this. And what we see is that the small list takes 0.004 seconds. The medium list takes 0.006, so that's 15 times faster. And the big list, sorry, 15 times slower. And the big list takes 0.5 seconds, which is 77 times longer than the medium list and 1,000 times longer than the small list. So the reason it's increasing by this much is because that's how much bigger the list is. The medium list is 10 times bigger than the small list, and since it's a linear relationship, it will also take 10 times as long. And whereas the big list is roughly 100 times bigger than the medium list and 1,000 times bigger than the small list, that's roughly the multiple that we see in terms of runtime. So with linear, the proportion that the input increases, that's the same proportion that the runtime will increase. This is our next example. It's a search function, a linear search function. And in this case, we are searching for a random number inside the list. So it could be the first element, it could be the last element, but it's a random element. So what would be the runtime of this function? Exactly. Worst case O of n, and yeah, O of n. Um, yeah, so that's correct. So typically in runtime, we talk about worst case. And in this case, the worst case is O of n. So let's see what happens if I run this. We see roughly that relationship. So it's very similar to the previous example where the medium list took 10 times as long and the big list took almost 100 times as long as the medium list. And this also kind of highlights that even though sometimes, like if we're running this 1,000 times, so in some cases, the first element was the element we were searching for, and we probably return the value much very quickly. But even then, the relationship we see is that it increases linearly. And that's kind of what matters to us the most is how does the function runtime increase as the input size increases. Okay, so here's another example. This is binary search. So as we mentioned yesterday, binary search does have a precondition that the list needs to be sorted. So in this example, I am creating new lists that are sorted, and then I'm running the binary search function. And just one note, I am also introducing a fourth list called the huge list. And this is, I believe, yeah, double the size, not double the size, exponentially double the size of the big list. So it's 10,000 times 10,000 is this number. So based off of our understanding of runtime, what should we see what do we expect the runtime to be? And what kind of relationship do we expect between A, B, C, and D? And maybe I didn't explain binary search yet, so I'll do that again as well. So binary search, the way it works is we have a list, and the way we search for our elements is we split the list in half. And if the element we're looking for is smaller than the element we see in the middle, we only search the left half. And the reason we can do that is because we know the list is sorted. So we keep splitting the list in half, and then looking on the correct side. And we keep doing that until we find our element or we're left with no elements to search. So the answer I'm seeing is log n, O of log n. Let me just see. So there's one guess that the huge list will take n log n, whereas the rest of the list will take log n. That's not exactly right because the runtime is based off of the algorithm and not the input. And with big O, we only care about the worst case scenario. So if there was any possibility for the runtime to be n log n, then all of the runtime for all of the lists would be n log n. What are we basing our search time on? So the way the search works is we're given a random number within the list. The list is sorted, and we need to find the correct element. And otherwise, yes, I'm seeing the answer log n, and that's correct. So if I'll go through an example. It will take a second, but we'll work through this. So if we have an array of size 1024, after the first step, we split the array in half, so we're left with 512 elements. Then the second time you split this up, it will be 256. And the next time we do it, it will be 128. Then it will be 64, 32, 16, 8, 4, 2, and 1. And when we're left with one element, we know either that this is the element we're looking for or the element is not in the list. And so going from 1,000 elements down to 1 took us 10 steps. So this is 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10. I was off by 1 by calculating, but this is roughly 10 steps. And the way we know that is because log base 2 of 1024 is 10. So the point is, as we increase the size, so if we go from 10 to 100 elements, or 100 to 10,000, or 10,000 to, I think, a million, or 10 million, the runtime will increase on a basis of log base 2. So let's see our runtime here. So the time it took to run on the small list was 0.0001, and the time it took to run on the medium list, which was 10 times bigger, was 0.002, or only 2 times longer. And the time to run on the big list was 0.003, or just 1.5 times the time it took on the medium list. And the huge list only took 0.009, or 2.8 times what it took on the big list. So the reason it works this way is because this is 10 to the power of 2, sorry, 10 to the power of 1. This is 10 to the power of 2. This is 10 to the power of 4. And I think this is 10 to the power of 8. So the exponent is what doubles each time. And so that's why we see the runtime roughly doubling each time. It's because the size of the input, the exponent was doubling. Oh, it might be 10 to the power of 6. Yeah, thank you. But yeah, that's kind of the power of log n algorithms, is that they scale very well with larger inputs. Okay, so this is our last example, and I will actually run this before explaining. This is a sorting algorithm. We looked at selection sort yesterday. This is another one. This is another algorithm called bubble sort. And although it was written here, what is based off of how we read the runtime of code, what would we expect this runtime to be? There's a question on where this code is. That's a good question. I haven't uploaded it yet. After the lecture, I'll be uploading it into the repository, and it'll be found in the O4 directory, this cohort directory. But typically this is going to be this is like the live coding session. So throughout this lecture, I'll be adding to this notebook, and then I'll upload it. I'll upload it at the end of the session. Okay, so yeah, so what is the expected runtime for this, and what relationship do we expect between A, B, and C? While people are answering, I'll just answer the second question. Just wondering, what is the window being shared? Jupyter on localhost? Exactly. I'm running Jupyter Notebook on my computer through the terminal, and then I'm accessing it through a web page.
Excuse me, Salar, just one request. I guess if you upload the code right now, we can follow with you. It would be more interactive, the session. If you can do that, that will be great.
Okay. Today it'll be take a bit of time because I'll need to make a pull request and then accept it. So what I'll do for future classes is make sure that these pre-lecture reviews are uploaded beforehand, and then I'll upload it again afterwards with that.
Exactly.
Yeah.
Yeah, it'll make it more interactive. Thank you so much. Thanks.
No worries. Let me just look at the answers. Okay, so if we recall yesterday, if we have code in front of us, the way that we can read code, analyze the code to figure out the runtime, is by looking at the for loops. So this for loop here runs from 0 to n. So this one will have a runtime of O of n. And inside this for loop, we have a second for loop. And this runs from O all the way to n minus I minus 1. So even though it is smaller than n, we still say this is O of n. Because as we mentioned yesterday, we only care about the highest order term and not the coefficients before it. This would affect the coefficient slightly, but it doesn't actually change the overall size of the term. So if we have O of n with a nested O of n, we saw this yesterday as O of n squared. So the runtime of this function is O of n squared. And what that means is if we 10x the size of our elements, if we 10x the size of our input, our runtime will actually 100x. So let's see what relationship we see with A, B, and C. So running on the smallest list, we have a runtime of 0.00006. Running on the medium list, it took 0.004, or 70 times longer than the small list. So even though we went from a list of size 10 to 100, which is only 10x, the runtime actually increased more than 10x. It increased almost 100x. And then when we went from this medium list to the big list, we saw a runtime of 55 seconds. Now that's an actual tangible amount of time to us because I had to wait roughly a minute for this to run. And this is 10,000 times slower than the medium list. So this function, as we mentioned, is O of n squared. And this is just demonstrating how quickly the runtimes grow as our input grows. We're doing a fairly simple operation. We're sorting a list, and our input size isn't that big either. It's only 10,000 elements. But even then, it takes a tangible amount of time just because of how inefficient this algorithm is. Okay, so let's move on to today's topic. Actually, I'll pause here for just a minute to see if there's any questions, and then we'll move on to today's topic. So we need to try and avoid that scenario. Exactly. Typically, again, it depends on your data set. If you're working with a small data set that's 100 elements, then it's completely fine to use an O of n squared algorithm because if it takes less than a second, it doesn't affect you much. But if you're working with larger data sets, then you really need to avoid these types of algorithms because they will cause your runtime to slow down a lot. Okay.
Can I ask a question?
Yes, absolutely.
Okay. So the zero, I mean O log n squared, right? That's the formula you used.
Sorry.
Sorry, did you say something?
Yeah, I didn't understand the first part of your question.
The formula that you used, right? Like n squared.
Yeah.
0 log n squared, correct?
0 log n squared?
Yeah, that's what you used.
No. So we haven't looked at log n squared. This function here is just n squared.
And n squared it's because it has two components.
Two nested for loops.
Two nested for loops.
Yes.
Okay.
The important part is that the for loops iterate through n. They depend on n.
I see. Okay. For the second for loop, you have 0, comma, n minus I minus 1. So
Yes.
0, comma, whatever the case is, n minus I minus 1, whatever that variable, it doesn't matter, right? That does not change the formula in this case, n squared.
Yeah. As long as we have n here. So even if this was like n over 2, the divide by 2 or the minus I, those don't affect the scale of n. And so it would remain as just n. We would interpret this as n when evaluating runtime.
Even if it's n square?
Sorry?
Even if it's n square?
So the n square we calculate using both for loops. So
No. I'm still sticking to the j, right? If the j value here
Yeah.
in this case n minus I minus 1, instead of n minus I minus 1, if it's n squared, would the formula be different?
Yes. So if this was n squared,
Yeah.
then this would have a runtime of O of n squared. This inner for loop would. And when combined with the outer for loop, it would then become O of n cubed. So
Okay.
we
I
have,
managed to digest it.
I'll repeat that again. So
Yeah.
the runtime, we evaluate the runtime for each line.
Right.
So if we start from the top, this first line, it is O of 1 because all it has to do is read the length of this array, and it can figure that out without having to iterate through the array. Python stores the length of an array in just a number. So this first line is O of 1. This second line, it runs n times because it's a for loop that goes from 0 to n. This line runs n times. So we say this line is O of n. This next line, it also goes from 0 to n. So this runs, this has a runtime of O of n as well. And I'll go quicker with this again, with these last two, but these both are O of 1 because they're simple operations. So I'll just write this here. And so now, if we have nested lines in Python, what that means is that the internal block for a for loop runs that many times, the same amount of times as the for loop. So that was a bit convoluted, but the point is this code runs n times because of this for loop. And this internal for loop also runs n times. So it runs n times n times, n squared. Because we have this nested for loop, and the outer for loop runs n times and the inner for loop runs n times, the runtime is n times n, which is n squared. Now, if the inner for loop, if it was from 0 to n squared, so if n was 10, then n squared would be 100. If n was 1,000, n squared would be 10, 100,000, or a million. In this case, this line would run n squared times. And because it's still inside this outer for loop, which is also running n times, this would be n squared times n, which is n cubed. One thing I'll note is if this was something like from 0 to n over 2, then technically this line runs n over 2 times. And if the outer for loop ran n times, then we would be running n squared over 2. But as we mentioned in last lecture, when representing these values in big O notation, we can get rid of coefficients and other terms like -1. So what we can write this as is just O of n squared. We can drop the over 2.
Okay, sounds good. And you mentioned inefficient code. That means that the number of for loops it has to run. That's why you're calling it inefficient.
Yeah, fundamentally, the reason I'm calling it inefficient is because the runtime is n squared, and n squared scales very quickly. So in our example, we saw that running on a big list took almost a minute. That's why I was calling this inefficient.
So you're calling it inefficient based on the runtime, or the runtime based on what we are trying to do?
Based off of the big O of the function, this O of n squared. If I'll pull up the other slides from yesterday. this picture kind of represents what I'm trying to say a bit better. This picture here. So we broadly categorized these three runtimes as inefficient. And these four as better. Yeah, a bit better. So these two are very good, and these two are reasonable. So that was kind of the rough classification that we came up with yesterday. And typically these three at the top, n factorial, 2 to the power of n, and n squared, we want to avoid because the runtime scales very quickly.
Okay, perfect. Thank you. I got my answers.
Okay, so let me just double check the chat to see if there's any remaining questions. It seems like Edward's answered most of them. Okay. Okay, so let's start with today's topic, which is looking at array-based data structures, and we'll also be looking at searching and sorting algorithms.
Hi, I have a question before
Yes.
moving on. Yeah.
Yep.
So, given that this bubble sorting is so inefficient, do we actually use it anywhere?
In practice, not really. In Python, we have sorted. Python gives you a sorting algorithm, and this is much better than bubble sort. So if you're working in Python, there's almost never a reason to use bubble sort. If you want to for any reason, if you're dealing with small arrays, you can use it and you won't notice much of an issue. But typically, if you just have like if you give this to sort it, it will sort it for you, and this is very quick.
So even for small arrays, so why would we use bubble sort if we have better sorting algorithms, right?
Yeah. One example, it's probably uncommon in data science, but one example is you're building a microcontroller, like a very small computer that's going to be embedded somewhere, and you don't have a lot of space for your code. So rather than building a complicated algorithm that takes up a lot of space in terms of code, if you can just write a sorting algorithm that's 5 lines, that might just be better for a very, very small chip that you're putting somewhere.
So it's not efficient in time, but it's efficient in space. We can say
In
that.
terms of, I wouldn't say in terms of space, because space more so refers to the RAM, like the amount of space the data structure takes in RAM, but it is efficient in terms of lines of code. That's not something we'll really talk about in this course, but in some like embedded systems, lines of codes or your code base, the size of your code base does matter.
The size of the code is equal to the RAM, right?
No. Code is stored in your storage, and then when you're running it, it gets stored into RAM. But it's not going to equal the size of your RAM. It's going to be a small component of your RAM.
Yeah, but number of lines of the code is like directly proportional to the RAM, right? So that's what you mean when you say that because it has not very like short number of lines, so we can use this as compared to any other algorithm, right? Because it would consume less RAM as compared to other algorithms.
That goes a bit too much into the details, and I'm not exactly sure because it depends on how the computer loads the program. If it's able to load chunks at a time, then it won't make much of a difference. But if it loads the entire program into memory, then it will need to load the entire program. It depends on whether the language is interpreted or compiled, and there's other things that kind of come up. But in practice,
So we don't use this algorithm as often, right?
sorry? Yeah,
We
bubble
use
sort
it.
isn't used very often. You typically don't need to use bubble sort ever.
Okay, thank you.
And thank you, Tom, for the clarification. That's helpful.
Salar, very quickly.
Yes.
When you do the simplifications of n divided 2, we say that it's n.
Yes,
These reasonings will be all the same reasonings of big numbers, like the mathematics we used to do with infinite. So it's always the same. It's like assuming that n is going to be huge.
yeah, yeah,
So they
Exactly.
come from there. This is what I'm saying.
yes. The asymptotic behavior. So yeah, assuming that n is huge.
Okay, got it. Thank you.
Okay, let me just check. Okay, so yes, moving on. Array-based data structures, searching and sorting. So today we'll talk a bit about what data structures are. We'll look at the definitions. So data structures versus abstract data types. There's a key difference that we'll be talking about. And then we'll look at different data structures that we have access to, including arrays, sets, dictionaries or maps, as well as stacks, queues, and other structures. We'll also look at a little bit more into searching, sorting, and then we'll end with hash maps. Okay, so let's first start with the definitions. So we'll be talking about two things. One is an abstract data type, and one is a data structure. The reason we have this distinction is because some concepts are generally useful and transcend any programming language. So, for instance, if I talk about an array, which is a list of numbers, this isn't specific to Python or C or Java. This idea of numbers in a sorted list transcends any programming language. And so it's useful to have this notion of abstract data types so that we can focus more on the kind of operations and what it can do rather than how we're going to actually implement it. So an abstract data type defines some kind of data and the operations that can be performed on it. And the reason we say it's abstract is because there's no mention of how the data is stored or how the operations work. So we don't mention the programming language. We don't mention what lines of code we'll use. We more so focus on how that data, on what the data structure is and what we can do with it. So it's concerned about what. On the other hand, a data structure is a concrete method of storing data and therefore also its operations. So for instance, a Python list is a data structure because it has a specific implementation. Another way to look at it is abstract data types is an idea of what it will be. And then the data structure is what actually implements those operations, has an implementation, and actually runs. So if we're just looking at arrays generally, that's an abstract data type. So that is an abstract data type. But if we say a Python list, this is a data structure. Now, this data structure implements the array abstract data type. So we can say this implements the array abstract data type. And because it implements it, it is now the Python list is a data structure. The value, as I mentioned before, is that abstract data types, ADTs, form a common vocabulary for computer scientists to discuss problems, and it allows us to focus on the design now and worry about the implementation later. So there's a couple of important abstract data types. The first that we'll look at is a set. So I will actually add some lines up here so we can work with examples as well. So the first is a set, and the characteristics of a set is that it is a collection of unique elements. And the operations it gives you is get size, insert a value without introducing duplicates, remove a specified value, and check whether a value exists inside the set. So let's create our set here. We'll call it set1. And we can define it like this. And this creates our set. Now what I can do is say set1.add 7. And now if I look at set1, I have 7 in it as well. I believe we could also define it using curly braces. Let me just double check. Exactly. So this is our set containing 1, 2, 3, 4, 5, 6, 7. If we up to 6, if we add 7, then we can see 7 has been added. If we try and remove an element using pop. Okay, not pop. I think it is removed. Yeah, it is removed. So if you try and remove an element, it removes it from the set. And we can also check if a number is inside the set by saying 1 in, this should return true. And if I do 3 in, it should return false. And the other thing about sets is that we can't introduce duplicates. So if I try and add 7 a second time, it won't throw an error. But if we look at our list, or sorry, our set, we only have a single 7. So running it multiple times won't add another 7 to it, it'll just stay the same. The next data structure we have, we're probably most likely familiar with, is a list. The characteristic of a list is that it stores an ordered sequence of elements. Okay, it stores an ordered sequence of elements, and there's no restriction on the fact that it's unique or not. So ordered means that the order matters, and sequence, there's no unique, so it means we can have duplicates as well. I'll just add one note about sets, is that there's no restriction on, there is no restriction on whether it needs to be ordered. So that means that it is unordered. So sets are unordered, meaning right now it showed me 1, 2, 4, 5, 6, or 7, but I can't expect 1 to always be displayed first. There's no restriction on that, so next time I print, it could be that it shows 2 first and 1 somewhere else. Another kind of consequence of that is I should not be able to do this. I am not able to say, give me the first element, because in sets, there is no first element. And yes, ordered is different from sorted. Ordered just means that there's a first element, there's a second element, and so on. Sorted means that the first element is going to be smaller than or larger than all of the other elements. That's not what we're talking about here. We're talking about ordered. So lists have a couple of operations. We can access elements by index. This is because it's ordered. Because it's ordered, we can access elements by index. We can insert a value at a given index, and we can remove a value at a given index. So let's do this. So let's say this is our 1, 2, 3, 4, 5, 6. And if I look at this one and I try and insert, I can say insert the value 5 at position, the value 3 at position 4. And if I look at list now, so the first element, this is the first parameter into that insert takes is the index I want to insert at, and the second parameter is the value to insert. So if I do dot insert, it inserts the value 4 at position 3. And if there's a couple of questions in chat, I'll answer them in just a moment. But if I try and remove something, I can do the same thing. So I can remove at a certain index. I will have to check if it's removed at. No, it might just be removed. Okay. So removing at a certain index is pop, and I just give it the position I want to remove, and it removes it. So if I run this again, it will remove 5, because 5 is now in the 4th position. And Accessing elements at certain indexes is also fairly easy. You just use the square brackets. So this we can do with lists, whereas this we cannot. Whereas this we can't do the same with sets, is what I should be saying. There's a question. So a list is an ordered set. Almost, I would say that a list is an ordered set that can also contain duplicates. The reason I emphasize the idea of duplicates is because that actually makes a fairly big difference on the runtime. And we'll talk about that close to the end of lecture. But yes, those are the two main differences between a list and a set, is order and duplicates. The next abstract data type is a map. So the key thing about a map is that it stores key value pairs, where each key needs to be unique and associated with only a single value. So for instance, we can say that a key is, let's just say it's Solar, and the value is the grade that I got in a class. So let's just say 90%. And then we can have a second person, let's say John, and John got 95%. So in a map, we have keys, which are represented first, followed by a colon, and then a value. And the main thing is that keys need to be unique. So if I already have a Solar in the map, I can't have a second Solar. And this key can only be associated with one value. The value can be anything, so we can make this a list, we can make it a string, we can make it anything, but there is only going to be one key value pair. So some of the operations we have is look up a value for a given key, insert a new key value pair, remove a key value pair, and update the value associated with a given pair. So let's take a look at take a look at these operations in Python. So in Python, let's say this carefully. So in Python, the implementation of the abstract data type map is done by a dictionary. So the data structure is a dictionary, the abstract data type is a map, and dictionary implements a map. So we create dictionaries in Python using squiggly brackets, and we input numbers. We input the key first, followed by a colon, followed by a value. And then I can do a second person, and let's do a third person as well. There we go. So that's our dictionary. We've created it, and now we can do our operations on it as well. So we can do dictionary. Let's first get a value. So if I write the key in our square brackets, I should get the value. This gives us our value. We can also change an existing value by just overriding it like this. And now we can see that the value has changed. Additionally, we can add new elements by just same way we would update. So we just add a new key, and then we can give any value to that key, and we will see that this now contains the new key value pair. And note again, this is not ordered. Right now it is showing it in the order that I've inserted it in, but that doesn't mean that this is the order of the dictionary. Dictionaries don't have anything. And lastly, we can also remove values. I'm not exactly sure what the syntax to do that is. Let's take a look. So if we use dir for an object, it will tell us all of the methods we have available. So here we can see we might need to use something called pop. So let's try pop. So that removes the value. And then if we look at it again, we have removed Susan from the dictionary. Let me just take a look at delete is also available. Delete is not a method for the dictionary. So pop is the way we would remove a key value pair from a dictionary. Delete item is available. Okay, so delete item might remove, you might be able to delete using the value rather than the key. I haven't used delete item, so I'm not exactly sure how it works. But yes. So that is our map. And the last abstract data type we'll talk about right now is called an iterable. Iterables are very kind of, they're a little abstract in the sense that we don't have too many operations on them, and they have a very specific purpose. So iterables store a collection of values, and the values may or may not be unique. There's no restriction on those, and there's also no order to them. But the operation it lets you do is iterate through the elements of the collection one at a time. So let's say I have a bag of marbles, and inside the bag I have a marble labeled 1, 3, 4, and 2. What an iterable will do is give me each of the marbles one at a time through the entire elements of the collection. So it might give me 2 first, then it might give me 1, then it might give me 3, then it might give me 4. But the key thing is that it'll go through all of the elements and it will give them to me one at a time. So I'll just break for just a second so I can plug in my laptop. Just give me 1 second. Sorry about that. I am back. Yeah, so let's take a look at an example of an iterable in Python. So the way we define an iterable is using the iter keyword. We'll call our iterable iter1, and we will give it a collection of items. I'll give it using a list, but we can also use a set or any other collection this accepts. I'm not sure what other ones it does accept, but if there are, it would take them. But let's just say I give it a bunch of elements, and this lets us create our iterable. Now, the only operation we have available for iterables is to go through the elements of a collection one at a time. So the way we actually do that is using the next keyword. So if we do next, it will give me 3. If I do next again, it will just give me 4, 5, 6, 7, 8, 2, and 3. And if I do it again, it will throw an exception saying stop iteration. So this is a very, very kind of specific data structure, and it's used in for loops. So the way for loops actually work is when we do for I in and then we give it something here, what Python expects is that this thing that we give it over here is we'll let the for loop go through each element one at a time. And once the stop iteration exception is thrown, for actually catches that exception and stops the iteration. So if you ever need to like implement a for loop with a custom object, if you just implement the next function, then you can pass that function into a for loop and it would work. I'll just repeat that one more time. If you have an iterable object, what that means is it implements the next function, then you can pass that object into a for loop and it will know how to iterate through it. So even if, for example, we create let's actually do this example. So let's say we create a custom class called a garage, and a garage has something called how do I do this? Let's do def garage, and this. Sorry, I forget how. I just need to recall how to implement a constructor. I believe it's this. And then self. So self dot cars is equal to, let's just say we have a bunch of cars. Honda, Toyota, Lexus, okay. So we have a bunch of cars. If this is our, let's just see if this works. Garage 1 is equal to garage. And then if I take a look at garage dot cars, garage dot 1, garage 1 dot cars, these are our cars. So now if I want to iterate through my garage, I can try doing this for car in garage 1, print car. But this will not work because it says garage is not iterable. Now we could technically do dot cars, but if we had kind of a more complicated data structure where it isn't as easy as just accessing an object, what we could do is implement our next function, which I think is implemented like this. And what we can do is say self.current duration is equal to 0. And what we can do is with self.current duration plus equals 1 and return self.cars at current iteration minus 1. And now and we'll also just throw if self.current iteration is equal to length of self.cars, then throw stop iteration. We should do something like that. For the time being, I'll just return 0. But let's try this. Now if I actually this won't actually work because we need this will otherwise go into an infinite loop. So what I will actually do is let's just try this. But let's run this. Let's run this. It'll do an infinite loop, so let's just do a return. Okay, let's try this out. I think we also need to potentially make it an iterable. Okay, so I think I'm missing something minor here. But essentially, if I made this inherent from the iterable object and then implement next, then it would work in the for loop. I'll take a look at this during the break and then I'll come up with a working example then. But the main thing is the iterable abstract data type. It just implements this one function called next, and it lets you iterate through collections one at a time. Okay, so the relationship between an abstract data type and a data structure, covering this, and Python list is not an abstract data type. The reason we know that is because we're specifying the implementation. We're saying that it's a Python list, but it is a natural implementation of the list abstract data type. So a list generally is an abstract data type. The Python list is an implementation of that. And the reason the Python list is not abstract is because the designers of Python implemented all of the list operations based off of how they thought it should be implemented. And different people will come up with different implementations. That's why data structures vary in terms of implementation, but an abstract data type is generally consistent across programming languages. Also, a single abstract data type can be implemented by many data structures. For instance, we could implement a list abstract data type using a Python dictionary. We could do this by storing the elements of a list using the key indexes as the keys in a map and the values as the values in the map. So let's actually do this this exercise. So let's say we're creating a class called our map list. So that's the name of our list. This is the name of our class. We'll create our init function. And then we'll say that our self.collection is equal to an empty list. And then the function, the method methods we want to have available is like that. Okay. Sorry that it just froze for a moment. The operations that we want to have for a list is insert, get, and remove. And right, let's also do print. So all of these will look a bit like this. And when inserting, we will have an item to insert and an index to insert at. And when getting, sorry, is lagging just a bit. Okay, getting will get something at an index, remove will also remove from an index, and a print won't take anything. Let's call it print array because print is reserved. So our collection will actually be a dictionary because that's how we want to do it. So when we want to insert at the certain index, what we can do is self.collection index is equal to item. And if we want to get a value at a certain index, we can return self.collection at a certain index. And if we want to remove, we can do self.pop, self.collection.pop at a certain index. And in order to print for an array, what we can do, sorry, it just froze again. What we can do is create a temp array equals this, and then length of our self.collections is our size. And then for I in range, length, range size. And then what we can do is temp array dot append self.collections at position I, and then print temp array. So if this is how we create our map list, we can do ML is equal to map list ML dot insert at position 0 and the value 1, and I'll just do a bunch of these. So that's inserting, and then if I want to print this array, print our map list, we can try this. I think I just misspelled something somewhere. It's collection singular. There we go. So now I've printed this as an array. Even though the data structure this class is using is a dictionary, for all kind of intents and purposes, it looks like an array. And if I was to implement the other functions like get item, this lets you subscript objects, so it lets you use the square brackets in order to get indexes. We could also implement, we would also have that type of operation for our object. Okay, and just to quickly go over this function here, print array, because this is a bit confusing. What I do is I create a temporary array. I get the length of my dictionary, and the assumption I make is that this dictionary has been filled in from 0 up to n. If we were to skip, for instance, 2, this would cause an issue because we would then have 8 in this position and the indexes would be off. But with that assumption, I then just iterate from 0 to the length of our dictionary and append each value stored at each key via the indexes. And then I just print the array. Okay, let me just see where we're at here. So yeah, so that covers abstract data types and data structures. Next, we'll talk about a few key data structures like Python lists, stacks, dictionaries. But I think this is a good time for a break. So we'll take a 10-11 minute break and come back at 7:20. If you have any questions, feel free to ask them in the chat or speak out. I will be here, so just feel free to ask. Could you kindly repeat the relation of ADTs and data structures? I'm not getting the implementation relationship. Okay, absolutely. So let me just check I'm unmuted. Okay, yes. So an abstract data type it doesn't have an implementation. It's more of an idea. So if I say I want an ordered collection of ordered collection of values where we have how the data is going to be stored on in the computer. It doesn't talk about how we're going to actually access the elements. Because of that, it also doesn't have any runtimes. Notice how when I say get size, we don't or insert a value, we're not talking about iterating through the list or accessing a specific value or specific index. We're just talking about the idea that we can insert a value. So if you want to implement a data structure, you first have to start with an abstract data type. You have to start with an idea of what you want to implement. On the other hand, a data structure is an implementation of an abstract data type. So now that we have an abstract data type, where we have our definitions of what we want to implement, when we now go to Python or any other language and we say, for example, class list, and we start implementing the main kind of distinguishing factor here is that I see my voice is being cut off. I think that has to do with my computer, I think, lagging a lot right now as well. Okay. Okay, what I'll do is just give me 5 minutes. I'll see if I can sort out this legging issue, and then I'll explain the difference between the ADT and a data structure again as well. Just give me 5 minutes. I'll see if I can do something about this. So let's start with the difference between an abstract data type and data structure. An abstract data type is abstract. What that means is that there's no associated implementation. It also means that there's no runtime complexity for its operations. It's simply an idea. Yeah, it's an idea of what the data structure should look like, what operations it should have, and what it should store. On the other hand, a data structure is the actual implementation of that abstract data type. So when we implement a data structure, or when we implement an abstract data type and create a data structure, that data structure will have a very specific implementation. It will also have runtime complexities. So if we're just talking about an idea of a list doesn't have searching in a list or getting the element of a list does not have a runtime. But if we're talking about a Python list, on the other hand, does have a runtime when we search or when we insert. And like one example of this is that a Python list, or let's say a list. Another option is by using something called a linked list. We won't be talking about linked lists in this course, but it's a way of implementing list-like data structures. And whereas inserting inside an array is O of 1, inserting inside a linked list is actually O of n. Actually, it's a little bit more nuanced than that. But essentially different operations do have different runtimes depending on the implementation. And that's what data structures covers. It's when you have a data structure, you have these different runtimes. An abstract data type doesn't actually deal with the implementation, so it doesn't have runtimes and other things. There's a thought in the chat. I guess another way to describe it is we talk about abstract data types, but we use data structures. For the most part, that's correct. We can also talk about data structures, but then we specific language and a specific implementation. But if we're talking about general lists, then yes, that's an abstract data type. And yeah, the use part is use data structures. Okay, so the first data structure we'll look at is Python list. Python lists. With Python lists, each element has an add.
Yeah, I think he dropped.
I am very sorry for my connection. I will try.
No worries, it happened.
I'll try turning off my video. Hopefully that should help a bit. But if it happens again, I'll try using a different network. And let me know if I do start cutting out. I'll see what I can do about that as well if it happens again. Okay. Yes, so with Python lists, what we actually have are when we create a Python list has an associated address. So let's say this is our list. The way that the list works, the Python list works, is that the start of the list has a very specific address. Let's just say it's OXB. So Let me see if I can, I'll use a different Wi-Fi and see if this helps. To a different Wi-Fi, hopefully this is more stable. If not, let me know. If it's worse, also let me know, I'll switch back. Yeah, so Python lists have an associated address in memory, and all the elements are stored in adjacent memory addresses. So if this is stored at, let's just say, OXB0, then the adjacent memory address is OXB1, let's just say. And then the next one is OXB2, and so on. And when we need to access, for instance, this position in memory, which this index in the list, which is index 3, the way we actually do that is by using the address of the list, which is stored in our program as OXB0, and we add 3 to it. So the index that we want to find, we add that to the address in memory, and that's how we get our access to the index or into the list. Have I disconnected again? Okay. Yeah, so this is how we access, this is how we, sorry, just losing my train of thought. Yeah, so this mathematical operation is how we access specific indexes in a Python list. And because it's a mathematical operation, it is an O of 1 access. This is how we achieve O of 1 accesses in Python lists. If we wanted to, for instance, there's a question, is this implemented with pointers? In the back it is, in the Python implementation it is, but when you're actually programming in Python, that's kind of abstracted away from me. If we look at appends, which is adding elements to the end of an list, a new address is created at the end of the list, and the index, the value is added to that position. So it's O of 1 time, because it doesn't matter how long the list is. All we have to do is access the address, add the length, and then access that address in memory and add the element to it. So the runtime for append is O of 1, because it's adding to the end of the list. On the other hand, the runtime for an insert method is different, because we have to look at the worst case scenario. And the worst case scenario is that we add to the front of the list. Because we're adding to the beginning of the list, and the address of a list can't change, what we would have to do is make space for that element. So let me actually erase everything so I can draw it a bit more neat. If this is our index, this is our list, and we've stored 2, 3, and 4 here. If we wanted to insert 5, it would be very easy if we wanted to insert it at the very end. We would just add it here, we would append it, and it would just be O of 1. But if we wanted to insert 1 at the start of the list, right over here where 2 is currently, we would first have to move 4 over, then move 3 over, then move 2 over, and then we would have the space to insert 1. Because lists are ordered and the order matters, we need to maintain that order. And if we want 1 at the beginning of the list, we need to make space for it. So because we have to shift every element over, inserting is O of n. So insert is O of n time, append is O of 1 time. If we wanted to delete an element, then, for instance, if we want to delete the element 2, which is at the start of the list, we would first remove it. And then because this space is empty, we would actually need to shift everything back as well. And so deleting is also O of n time. because we need n operations in order to delete an element in the list. Let me actually undo that and just erase these. What about pop? So pop is another method for deleting an element, but in the case for pop, it deletes the last element. So if we have 2, 3, and 4, and I call pop on this, it will just delete 4. So what is the runtime of that function? Exactly. It's O of 1 because there's no shifting that needs to be done in order to adjust the list or to make sure that it's a valid list. Okay, let's move on to another abstract data type called stacks. So a stack contains 0 or more items. And the key thing about a stack is it has 2 operations. One is called pushing, where items are added to the top of the stack, and popping, which is items are removed from the top of the stack. We can kind of visually think of it as a stack of dishes. So let's say I have a sink here and I put a dish on, I want to put a dish on the counter. I would put the dish at on top of the counter. Now, if I have a second dish, I would put that dish on top of the first dish. And I would make like a stack of dishes this way. And if I wanted to remove a dish, I couldn't remove from the middle. The only way to remove a dish is by grabbing the one on top and taking it off. So in a similar way, stacks do the same thing. So if we have a stack, let's draw it like this, and we want to push 0 onto it, we would add 0 to the top of the stack, which is right here. And then if I wanted to push 2 on top of the stack, I would add 2 to the top of the stack. And then if I want to push 4, I would push 4 on top of the stack as well, and it would come over here. Then if I wanted to pop, I couldn't pop anything except 4. Like if I wanted to access 0, for instance, I couldn't access 0 in any other way than first popping 4. And then once 4 is removed, then popping 2. And once 2 is removed, then I can finally pop or access 0. So because of this, this kind of structure, the first item added to the stack is also the last item removed. So the 0 was the first item that was added, and it will be the last item removed. We call this behavior first in, last out. So the first in is the last out. We also can call it FILO, F-I-L-O. We can also say the last in is the first out. So that would be LIFO. So both of these refer to the same idea, and it can be used to describe a stack, which is first in, last out, or last in, first out. Yeah, that's a good example as well, a one-door elevator, where the last person in is also the first person out. Can you explain the stack of dishes example again? Yes. So the way a stack works is that we only have 2 operations. We can add to the top of the stack, and we can remove from the top of the stack. So an example of this in real life of a stack is the dishes. So when you have dishes, generally you can only add the dish to the top of the dishes. You can't really add dishes. If you have a stack of dishes, it's tough to add a dish to the bottom of the stack. You would have to lift everything up, and generally that's not done. Generally what you do is you have a dish, you add it to the top of the dishes. And then when you're washing these dishes, you typically grab from the top of the stack and wash that top dish. Let's call it a plate. So that top plate. So in the same way, in the same order that you would do the dishes in real life is the same way that the stack operates. There's a question, where is the stack used? There's lots of places it's used in programming. A very common example, or a very prominent example, is the back button in your web browser. So let's say you visit Google. From Google, you visit YouTube. And then from YouTube, let's say you just visit Facebook. Let's actually add one more. Let's say you then visit LinkedIn. So let me just write this out, LinkedIn. Okay. So you visit Google. What the web browser does is add Google to your stack. And then when you visit YouTube, you add YouTube to your stack. And then when you visit Facebook, you add Facebook to your stack. And this is your history essentially. And when you click the back button, which means that go from LinkedIn back to Facebook, all the web browser has to do is pop the last web browser you visited, which is the top of the stack, and you can just go to Facebook directly from there. And then if you press back again, all you have to do again is just pop the stack and grab the last web page you visited, which in this case is YouTube. And so it kind of maintains the logical order that you would expect with a back button, just inherently through the data structure.
So I have a question here.
Go ahead.
Yeah, is it a data type or a memory? Because I have heard stack and heap in terms of memory.
Yeah, so the stack in terms of memory is a different concept. And tomorrow we'll actually be talking about call stacks, which use the stack structure, but it's used in programming languages. But in terms of the memory stack, that I believe does follow the same structure as this, but it's a different concept in terms of how it's in terms of where it's
So
used.
this is a data type. This is not related to the main memory, right?
Yes, this is distinct from the concept of a memory stack.
Okay, thank you.
And yeah, this is an abstract data type, but if we implement it in a language, then it becomes a data structure. Okay, and yeah, there's a couple of examples of other uses for stacks in the chat. Those are good examples. And yeah, those are yeah. There's a fun little question here that we'll spend 2 minutes on this. Is it faster to use the front or back of a Python list to implement a stack? And what is the big O for stack operations under each choice? So we'll actually spend 2 minutes. So we'll talk about this at 7:40. But do think about this and try and reason for which one is faster. Okay. Yeah, I'm seeing lots of great answers in the chat, and yeah, all of those are correct. So it would be faster to use the back of a Python list because if we use the front of a list, we would need to shift all the elements either to the right when pushing or shift them to the left when popping. And those operations are O of n. But if we use the last element of the list, the back of the list, as as where to push and pop from, then we don't need to do any shifting and it will be faster. Okay, the other kind of structure similar to a stack is called a queue. And A queue again contains 0 or more items. And in this case, we again have two operations, but the operations are slightly different. So items are added to the back of the queue, and this is called enqueuing. And items are removed from the front of the queue, and this is called dequeuing. So this is very similar to kind of what you would expect in real life with queues. If we imagine like a line at the bank, when you enter a queue, you enter from the back, but you enter from the back, and the people that leave the queue are from the front. So if this is the front and this is the back, people come in through this direction and they stand in line, and people leave in this direction. So the first person to arrive is the first person to leave. The second person to arrive is the second person to leave as well. So we call this first in, first out. So FIFO. I've also heard LILO, but this is used to describe queues. So we'll spend a bit less time than the previous question on this. Is it faster to use the front or back of a Python list to implement a queue? What is the big O for stack operations under each choice? There's a question, what is the use of a queue? Again, there's lots of different uses. One example is the print queue for a printer. So typically the way printers work is that you have multiple computers. Let's just draw this is a computer. Let's say you have 3 computers in your network and you have 1 printer. Let's draw a printer. So computers send jobs to printers, like let's print document 1, let's print document 2. This person wants to print document 4, and that one wants to print document 3. So typically the idea of queues is it maintains the order that things come in. So let's say that this computer first sent in document 2, then this person sent in document 4, this person sent in document 3, and then finally this person sent in document 1 at the very end. So we would want the printer to print document 2 first, followed by document 3, then 4, and then 1. So if you use a queue to organize the jobs, then the printer will make sure to print in the same order that items come in, and that's kind of what the users would expect as well. So this is an example of where a queue is used in programming. Another good example is call center calls. That's a good example as well. In the chat for the practice problem, I'm seeing lots of good answers. And yeah, both ways is actually the same, because if you enqueue in the front, which is O of 1, then you would if you enqueue in the back, which is O of 1, then you would have to dequeue from the front, which is O of n. And if you did the opposite, then you would again see the O of n behavior for the other operation. So either way, we need to shift elements. And so in this case, it doesn't really make much of a difference. If we wanted to be a little bit kind of technical, we could say that the number of enqueues will always be greater than or equal to the number of dequeues, because you can't dequeue unless you've already done an enqueue. And if we really wanted to be very, very kind of specific, we could say, let's make enqueue the more efficient operation, because that number will always be strictly greater than the number of dequeues. Would you need to decide size in advance if you do the opposite? So in Python specifically, you don't need to decide the size of the list, because Python kind of does that for you. But no, I don't think you would need to decide the size of the queue in advance. Let's walk through an example. So let's say we have two elements. Sorry, we have two queues, one implemented one way, one implemented the other, and we want to insert 0 followed by 2 followed by 4. So if we were to insert 0 into this list, it would just come in the front of the queue, same with this one. If we wanted to then insert 2, in this example, it would come here to the back of the queue. In this example, 0 would shift over here, and this would now contain 2. Now, if we were to dequeue 0, in this example, we would just remove 0 and it's gone. We don't have to do anything. In this case, we would have to remove 0 and then shift 2 backwards. So I think in either case, the length of the queue doesn't need to be figured out beforehand. Python kind of just handles that in the back end. It dynamically increases the size if you need it, but both operations I think will work. Okay. Okay, let's move on to searching. So yeah, we just covered we covered one data structure, Python lists, and two abstract data types, stacks and queues. And let me just see how much content we have left. Okay. For tomorrow, I will also implement the stack and the queue in Python just to show how that would work. Feel free to practice that in the meantime, but because of time constraints today, I'll leave that for tomorrow's review. Okay, let's start with searching. So we'll start with a motivating example of we want to develop a machine learning method to search through a video and figure out when a bike is stolen. So one option we have is we could start from the beginning of the video feed and run our machine learning model on every frame until the bike is no longer in the frame. And that's when we know that the bike is stolen. And this would take O of n time. And because this is a machine learning model, it might take a very long amount of time because machine learning are computationally heavy workloads. But what if we started halfway through the video, and if the bike was there, then we could break the remaining video in half and only look at the previous chunk, the first half. Because the video is still there, if the bike is still there, we would look at the second half because we know it wasn't stolen in the first half. And then we would check the halfway point of that second half. And if the bike was still there, we would look at the next half as well. And we would keep doing that until we find where the bike was stolen from. So this approach is called a binary search. We've talked about this a couple of times, but this video is a nice way of thinking about it. So how many steps does binary search take when searching through 100 numbers? And how about when searching through 10,000 numbers? So to search through 100 numbers, I think it's roughly eight steps. If we do log base 2 of 100, we'll get the exact number. But I think it's roughly 8. And then for 10,000, I think it's roughly 15 or 16. So binary search is O log n, and that lets you tackle very big numbers in very few steps. Whereas the big O of linear searching is O of n. So to search through 100 numbers, it would take 100 steps. To search through 10,000 numbers, it would take roughly 10,000 steps. Just one kind of notice is that binary search requires that the list be sorted in advance. And in our example, we were able to implicitly assume this because time is kind of sorted. If we have a video stream, that is implicitly sorted. There's a question in chat. Can we get access to the Jupyter notebook so we can follow up? Yes, I'll upload this notebook after the session. For future sessions, this will be uploaded beforehand. And moving forward today, everything that is coming up here, you should also have in the already uploaded session, uploaded notebook in the repository. everything that's coming forward is already uploaded. Okay, so yeah, we've touched on binary search and linear search already a couple of times, so we kind of went through this a bit quickly today. But yes, linear search is O of n, binary search is O of log n. Binary search works very well on large data sets. It just requires that the data set be sorted. There's two sorting algorithms that we'll look at here. One is selection sort, which we looked at yesterday as well, and then the other is insertion sort. The way selection sort works is, suppose you want to sort prices of all the fruits at a supermarket from lowest to highest. So you're in the fruit section, you have a bunch of fruits, and you want to sort them from lowest to highest. One approach is that you walk through the entire row of fruits, keeping in mind what the lowest price you've seen is. So for instance, if you first come across avocados, which are $4 a unit, and then you move on to apples, which are $1 a unit, and then you keep in mind the cheapest price you've seen. So it was first at $4, then it was $1, then bananas are 79 cents. So you remember bananas, and then you get to the last fruit, which are pineapples, which are $5. So you found the lowest priced item, which is bananas, and you are able to kind of grab that or put that in the first position as the cheapest item. You then go through the entire row of items the second time, this time looking for the second lowest item, or you look for the lowest item, but you skip bananas. And you keep doing this for each fruit. So if there's n fruits, you have to go through the rows n times, looking at all n fruits. After you've gone through the row n times, you'll be left with a sorted list of fruits. But if we think about how many steps it takes, in order to find the lowest price in a row, you need to look at n fruits. You need to look at the entire list. And you also have to do this operation n times in order to find each of the lowest fruits, like the first lowest fruit, the second lowest fruit, third lowest fruit, and so on. So if you need to do n operations n times, that is n times n runtime, which is O of n squared. So intuitively, that's where the O of n kind of runtime comes from. The other approach we have is called insertion sort. And the way insertion sort works is that we compare the current item to its predecessor. And if the item is smaller than its predecessor, then keep comparing it to the items before and moving it down the array. So this one's a bit easier to understand with this example. And so let's take a look here. So we start with this list that is 4, 2, 6, and 0. We know a list of size 1 is already sorted. So we start with this list of size 1, knowing that it's sorted. And we look at the next element. In this case, our next element is 2. And we compare it with the first element or the last element of our sorted list, which is 4. If it's greater than it, then we keep it where it is. But if it's smaller, we swap the two positions. So we swap 2 and 4, and we're left with 2 and 4. And because now we've arrived at the end of our list over here, we've sorted this sub list of elements 2 and 4. We then look at the next element, which is 6. Because 6 is greater than 4, 6 is already sorted, and so we increase the size of our sublist to also include 6. Now we need to sort 0, which is our last element in our full list. We'll compare it to the last element in our sublist. In this case, 0 is smaller than 6, so we would swap these two. So in this intermediary step, this is now 6, this is now 0. Now we compare 0 and 4. In this case, because 0 is less than 4, we also swap these. So this becomes 4, and this becomes 0. And then we compare again. If in this case 0 was greater than 2, then we would have a sorted list and we would stop here. But because 0 is less than 2, we would swap these once more. This would become 2, this would become 0. And now because we've arrived at the end of our sublist, this is now our sorted list. So this is how insertion sort works. And because we need to potentially traverse the entire sublist for each element, this is also n squared. Because we need to traverse the full sublist, which can be n elements, and we do it for n elements, it will be n times n. Okay, let's move on to the next example. This is a live coding example where we will implement this problem using we'll implement this problem and then we'll analyze the runtime for this problem. So this is saying that the H index is defined by Wikipedia as the maximum value of H such that a given researcher has published at least H papers that have been cited at least H times. So given a list of integers representing a researcher, each index is their ith publication and the value of their ith index is the number of citations. So calculate the H index of that researcher. So if we have this example, for instance, where it's 2256, what that means is the first publication the researcher had, they had 2 citations on it. Then the second publication the user had, they had another 2 citations. Their third publication had 5 citations, and then their most recent publication, their fourth publication, had 6 citations. So they have 4 citations overall, and in this case, their H index would be 2, because they have 2 publications with 2 citations, but they do not have 3 publications with 3 citations. If they had 3 publications with at least 3 citations, then this would be considered an H index of 3. Okay, so let's implement this function. So we'll call it find H index. And the first thought I have is I need to basically evaluate what the H index of this list is, and the maximum value for this list is 4, right? Because for a author to have an H index of 4, they need to have 4 publications with at least 4 citations. So if they only have 4 publications, that's the max H index they can have. So intuitively, what I'm thinking is I first need to evaluate this list to check if they have an H index of 4. If they don't, then I want to evaluate it for 3, and if not, then 2, then if not, then 1, and if not, 0. So let's first let's first just pull the size of the list. So the size of the list is this. And then I want to iterate from 4 to 0. So for I in range from 4 all the way to 0. So let me just double check that this works. So print I, and then let's call find H index and list. So let's remove that. So I would expect to see 4 all the way to 0. I might have to add a -1. There we go. Okay. So from 4 all the way to 0. We'll just do 1 because if it doesn't evaluate 1, then we'll just return 0. Here at the very end. My laptop was lagging. Did I cut out for any bit, or was I clear all throughout? Okay. Okay, so now what I want to do is essentially count the number of publications that meet my requirements. So right now I'm evaluating for an H index of 4. So I want to count the number of citations I have that is greater than 4. Let's say count is equal to 0. I'm not exactly sure why this is red. Okay, so for j in range list, if j in, sorry, not range, let's just do for j in list. If j is greater than or equal to our I, which is 4, because we're evaluating if they have an 8 index of 4, then we will do count plus equals 1. And then what we will do is say if count is equal to j, then we want to return j. Sorry, I'm saying j, I want this to be I. Return I. So I want to count how many citations the researcher has that have 4 or more citations. So that's this variable. And if this variable ends up equaling 4, I know I want to return 4. And if I get through this entire list and I don't have a count equal to 4, then I want to update. I will reduce I by 1. I will set count to 0, and I'll redo the same thing, except now evaluated for 3. So I feel like this should return the right value. And yeah, it does. So now if I was to just add another publication that had three citations, now this H index should be 3. And if I do that, I get 3. If I was to update this to be 4 and this to be 4, I would expect 4. Yeah. So this is working as expected. And now we would want to also evaluate the runtime for this. So what is the runtime for this function? O of n squared is one answer. Yeah, so looking at this function, we would look at the for loop to calculate the runtime. So we have this one for loop that from 4 to 0. Now in my case, I did 4. It should actually be that's a mistake on my end. This should actually be size. So it iterates from the size, which is the length of the list, so that's n. And this is for j in list as well, so this is also n. So we have n iterations here, we have n iterations here, and because they're nested, this would be O of n squared. And there's a question, can you go over the 3 and 4 example again? Yes, I can. So let's first bring this back to the original example. This was the original example. So the H index is the maximum number of publications that also have the same number of citations. So an H index of 4 means that they have 4 publications, 4 publications with 4 citations. So these represent the different publications the user has, and each number represents the number of citations. So, so if we look at these 4 publications, it has 2 citations, 2 citations, 5 citations, and 6 citations. So we don't have 4 publications with 4 citations, at least 4 citations. So then we evaluate for 3. We don't have 3 publications with at least 3 citations. So we evaluate for 2. We do have at least 2 publications with 2 citations. Now, if I was to add 3 to this this index, sorry, this list, now the user has in total 5 publications, and in those 5, 3 have at least 3 citations. These 3 have 3 citations. So this would be considered an H index of 3. if I update this publication to have 4 citations, now we have, sorry, I would also have to update this. So now we have at least 4 publications with 4 citations. This has 4 citations, this has 4, this has 4, and this has 4. So this would be considered an H-index of 4. And so if we run this, we do see our output to be 4. And yeah. Let's, are there any questions about this?
Yeah, I have. So until now, we studied like 3 types of sorting algorithms, insertion, selection, and bubble sorting, right?
Yes.
So all of them are of the order of n square.
Correct. Yep.
So like which of them is better, which one should we use, and like what is among these, Python sorted function uses which one of these?
Okay. So you should be using sorted. There's no situation practically where you should be using insertion, selection, or bubble sort. You should just be using sorted. In terms of what sorted uses, it uses, I think, a combination of quick sort and insertion sort. It might be actually merge sort. This one I'm not too sure. I don't recall too clearly. But it's one of these two and insertion sort as well, depending on the size of the list. So it does lots of clever optimizations in order to make it run quickly. But the main thing is it uses very clever tricks in order to sort things quickly. You should just be using sorted, or if you're using pandas, you have a function called like if you have a data frame, I think you can do something like sort values and specify the column. In NumPy, there's probably something similar where you can do np.sort, maybe sorted or sort values. I use NumPy a bit less, so I'm not off the top of my head, I'm not sure what this is. But these are the sorting functions you should be using. You should not implement your own sorting functions because those have already been done by other people. And those are much quicker than anything that I can or that you can implement.
So we shouldn't be using any of these 3, right?
Yes. Correct.
Okay, and my other question is like the last example which we discussed about the H index. So how is this example related to the sorting? Or is this
This is
related?
related to sorting. There's 2 goals for this live coding problem. One is to basically evaluate the runtime of this function. And the other is kind of the mindset that you need to have in order to approach solving these types of problems. Because this type of problem is something that you can be asked in a live coding, sorry, not in a live coding, in a technical interview. They might give you something like this and ask you to implement the function to do it and then report the time complexity. That's the type of kind of questions you might be asked. So the purpose of this is to kind of guide you on how you think about the problem.
Okay, so the goal is like if we are implementing a code or a function, we should know how much runtime is that particular function is taking, right?
Yes, you should.
Okay, thank you.
Okay. Could the H-index problem be solved with an ON solution? That's a good question, and that's an example of a question that you can be asked in a technical interview as well. Is you come up with a solution and then they'll ask you, can it be solved in a more efficient way? If I think about this, there could be some techniques. So one thing I'll preface my answer with is typically in interviews, they also want to know what you're thinking. So just a good interview, kind of a good interview advice is think out loud. If you're thinking about something, talk about it so that the interviewer also knows what you're thinking. Generally that if you're thinking on the right track, they tend to be impressed and they tend to guide you as well. So my first thought when thinking about whether this could be done in a more optimal way was it'll be tough because we need to look at every element while also considering whether which index it falls into. So which age index it falls into. There's a question, can we use list comprehension for this? List comprehension is just a way of expressing a for loop in a way, in a sense. So potentially, but I don't know if a list comprehension would be more efficient. But what I did think, well, what I am thinking now is, what if we iterate through this? What if we iterate through this list and maintain something in a dictionary? So if we have an index 2, what if every time we see a 2, we do a plus equals 1 here? And then every time we see a 5, we do a plus equals 1 here. And by the end, we will have something that looks like 2, 5, and 6. And then so building this dictionary took n time because we iterated through everything once and we came up with this type of dictionary. Now I want to iterate through it again, but this time in reverse. And what I will do is add these values, or keep adding these values. And if these values are greater than the keys, then I know that the solution is, then I know that that is the H index. And this is just 2n operations. So we can actually, let's try and implement this and see how it works. So we will. So there we go. Okay, so let's iterate through our list. So for I in list, we will do if I in keys, list dot keys. Actually, okay, so what we'll do is for I in list, we'll create a dictionary and we will do d sub I equals to 0. Okay, this is just to initialize our dictionary. Then in our second iteration, what we'll do is plus equals 1. And then in our third iteration, okay, so this is a bit of a problem because I intuitively just said we will go through this in reverse, but keys aren't sorted. So what we would actually have to do is create a new thing called keys is equal to d dot keys. We can then do sorted keys is equal to sorted keys. And this is n log n. So we don't have n runtime anymore, but we do have something better than n squared still. Then for I in sorted keys, actually, I think I want to reverse this as well. And let me just double check that this works the way I want. So if I give this 1, 2, 3, I would expect 3, 1. Okay. So for I in keys, then I can do d sub I, total count is equal to 0. D sub I, total count plus equals d sub I if total count is greater than or equal to I, then return total count, return I. So let's try find 8 index 2, and let's just do this. So yeah, this might be working as well. And in this case, if we evaluate the runtime, we can say that this is O of n. This is O of n. This is also O of n, or just O of 1. This is n log n, because we're sorting the list. And then this is just a single for loop, so this is O of n as well. So technically, this implementation is faster than this implementation. And if this was an interview, I would now start thinking out loud if there was a way to avoid this sorted step and do something clever in order to figure that out. One option actually is to just get the length of the list and iterate from range n to range 0. There's no need to actually sort the keys. So I could also implement that, and that would actually get us O of n as well, I believe. But yeah, that's kind of the approach you would take in order to work through this. Exactly. There's a question, because for loops are not nested, we get a better result. That's exactly right. This is O of n, this is O of n, and because they're not nested, it actually just becomes n plus n, which is just 2n. And then yes, the n log n, we also add. And if we were representing this in big O notation, we would actually get rid of the n2n, so it would just be n log n. But yes, I think we can actually implement this in O of n time as well, if we're able to get rid of this step, which I think we can. Okay, there's 13 minutes left, and we still have a fairly important section to go through, which is hash maps. So we'll spend the next 13 minutes on this, but then we will also spend the beginning of next lecture on this as well. So let's start with the motivating example, which is, if we recall from last lecture, the Python set took basically 0 seconds when we were trying to search for an item. Let me just pull that up here. Up here, when we compared searching in a set, we saw that a set search almost took close to 0 seconds, whereas the list search took much, much longer. And we said that we will look at how this works later. So the way it was able to achieve O of 1 time was through something called hashing. So what hashing lets you do is immediately know where and what the item is. It lets you directly access it. And the way it does that is through a clever function called a hash function. A hash function is a function where when you enter a string, it returns an integer. So for instance, this is Python's hash function. We input any string and it gives us an integer. And there's 2 requirements for a hash function. One, it needs to be consistent. What that means is if I run this again, I should get the same number, which I do. And the second requirement is that different words need to map to different numbers, meaning that each string has a unique hash. So even if I just add an exclamation point at the end of the string, I should get a completely different number, which I do. A second exclamation mark, a completely different number. So those are the 2 requirements for a hash function. Now, the way we have this example here, but I will first explain it in a different way for the sake of time. Now, let's say we have a list of size 10, okay? So in order to represent this list of size 10, I will just add 10 elements. These are 10 elements. Now, if I wanted to store this value, ds for life, in this list, my approach would be to use the modulo operator with the size of the list. So length list. And this will give me a number from 0 to the length of our list, in this case 10. And if I gave it a different function, if I gave it a different input, it would give me a different number. So each string will give me a different number, will give me a completely different number, like this. And when I modulo it, it will be reduced to something between 0 and 10. Now, when we do the modulo, it does introduce hashes that can clash with other hashes. For instance, let's see if we can find one. Okay, there we go. So I believe both of these strings hash to the same number. So doing modulo does kind of restrict our space a bit. Like it does cause something we call collisions, but we'll see how we address that in a moment. When we do the modulo with the length list, it actually gives us something that we can use to correspond to indices. So what we can say is list at this index, this function that I have here, set it equal to my value. In this case, it's SAL. And what this will do is store our value in the 5th position. And now, if I ever need to find out if this value is stored in my list, all I have to do is use this hash function. So I will use this hash function with the list. And if this returns the value, it means it's stored in my list. And if it doesn't, for example, if I look for this value, I get a 0. This means it's not stored in my hash table. So the hash function is an O of 1 operation. And because it's an O of 1 operation, and it tells you directly which index the element would be stored in if it was in the hash table, and then you can directly access it to check if it is stored, it lets you achieve an O of 1 searching. It lets you achieve O of 1 searching. And a set, which we looked at yesterday, it uses hash functions in order to sort in order to store data. And that is why it can't hold duplicate values, because duplicate values would have the same hash value and it wouldn't be able to distinguish one from the other. Does that make sense so far, or should I answer any questions about this so far? Okay, so this was not clear. Okay. Lost me at mod. Okay. Hash changes when the length of the list change. Here the length has to be known constant or known beforehand. Good question. So I'll answer the last 2 questions first. Does the hash change when the length of the list changes? Yes, it does. And so if you need to change the length of a hash table, you do need to reorganize all your data. Here the length has to be constant or known beforehand. Yes, it does. When a collision occurs, will it create a nested list in that index? Yes, that's one way of resolving a collision, is by creating lists instead of elements. Let's start from the beginning. We'll also cover this tomorrow, so there's no pressure in trying to understand this today. But let's first create our own function, hash function. So def hash function, and it will take in our input. Let's just call it INP, and we will also just pass in a size of our hash table. What our hash function will do is pass our input to a hash function and modulo it by size. And if we now break this up, if we try and take a look at what this does, if our input is my name and we pass that into a hash function, we get some random number, and this number is consistent for this input. if I modulo it by 10, what this will do is, what modulo does is it divides it by the number and takes the remainder. So if this is our number and I divide it by 10, I will get this number with a remainder of 4. And so what mod 10 does is just return this remainder value. So that's why we get 4 here. The benefit of modulo size is that it limits the value of the hash to be between 0 and whatever your modulo value is. In our case, it's 10, so it will limit the value to be between 0 and 10. And once it's between 0 and 10, we can use this number as our index. So let's get rid of this and let's just call our hash function on Solar. And let's also say the default size is 10. So if I call hash function on Solar, I will get 4. If I call hash function on John, it will be 9. Yes, the remainder will be between 0 and 9, and that is what corresponds to our index, because our indices are also start from 0. So these numbers that are now coming out of our hash function correspond to indices. What that means is in our collection, whether it's a list or something else, we should store the value Solar in position 4. And we should store John in position 9. So if this is our list, what we can do is say store, like if the value that we want to store is Solar, what we can do is say list, actually let's call this a hash table, HT. HT, we first want to get the index that we want to store in the hash table, so we will use our hash function, pass in our value, which is Solar, and we will say this is equal to our value. So now if you look at our hash table, it is filled with zeros except for where we inserted Solar, that contains our value. And now if you want to insert John as well, oops, sorry, this. Now we have John stored at 9. So this is how we insert into a hash table. We use the hash function in order to get the index, and then we store that value at that index. Now, the value here is if we want to check if Solar is stored in the hash table, what we can do is say this. So at the index where John should be stored at, is that equal to John? And if it returns true, it means it is stored in the hash table. And if it returns false, it means it is not stored in the hash table. Now, if we look at what operations we're doing in order to do this insertion and membership check, all we're doing is using a hash function, which is O of 1. We're doing modulo, which again is O of 1. And we are doing an array access, which again we know is O of 1, because it's just adding a number to an address. So all these operations are O of 1. And we're able to now search inside a list in O of 1 time. We will repeat this again tomorrow, go through it a bit slower, and we'll build a full working example as well. I'll do that before lecture and upload it before lecture as well, so you guys have that available. But this is kind of the main idea of a hash table, is by using this hash function, you can directly figure out which index the item should be stored in, and all the operations in order to then evaluate that are O of 1. Okay, we've hit time for today, so I'll stick around for a couple of minutes to answer questions. But otherwise we will cover this tomorrow as well. And yeah, the main thing I want to talk about, the main thing I want to also just mention before we end is you do have all the necessary content covered in order to start assignment 2 now. So feel free to start assignment 2. And yeah, we'll do a recap of this tomorrow as well. I will start looking at questions as well. Yeah, Edward's answering the questions, so that's great. Otherwise, yeah, thank you everyone. Today was a bit rougher with the internet connections and the laptop issues, but hopefully the recording was consistent, and I'm happy to answer questions now as well as tomorrow. Have a good evening, and yeah, take care. So what's the thought process for building our own hash function in such a way that collisions are avoided or handled? So building your own hash function isn't something that you'll most likely need to do. Python implements dictionaries. It also implements sets. Both of those use hash functions and lets you do things in O of one time. So in practice, you don't typically need to use your own hash functions. But in terms of what's the thought process in avoiding collisions, it's the idea is if you do have two values that are going to be stored at the same index, you want to store them in such a way that you're able to then figure out which you're still able to figure out which element is which elements are stored here and which one if someone is asking if this element is stored in the hash table, you should be able to figure that out. It does add a bit of complexity because if you have two elements stored in the same position, you might need to store them in a list and then iterate through them. And that iteration does add runtime complexity as well. We'll discuss that a bit tomorrow as well, but yeah, that's kind of the main thought process in handling collisions is we want to be able to figure out if that element is stored there, even if there are multiple elements stored in that same position. Yep, you can start assignment 1. Assignment 2, you should be able to start after next Tuesday, as Antonio said. That's correct. I may have misspoke. If I said assignment 2, I apologize. I meant assignment 1.
Do you have some time to talk about something about the assignment?
Yes, I do.
Okay, so Hashleaf, I mean, is this a Python library?
Let me take a look. Hashlib, yes, that's a Python library.
What does it do?
It's basically as we looked at today, we have hash.
Yeah.
But the issue with hashing is, for instance, if I run hash right now, I'm getting minus 3 something. But if I reset my kernel, if I have a new Python instance, I will get a different number. So this is an issue because if you run this code, you're going to get a certain number, and then when I run the code, I'm going to get a different number. So we're using this hashlib library, which is going to consistently give the same number. Whether you're putting the number in or whether you're putting the string in or whether I'm putting the string in, we'll get the same answer here. But essentially, it is doing the same thing that we just did with hashing.
Okay, so it's every time a unique number is generates, right?
Sorry?
Every time it generates a unique number for any specific string. Is that what I understood, right?
Yes. So for instance, if I put your name in here,
Yeah. Suppose we do, yeah.
I get 1, and you should also be getting 1 if you put this number in. But if we were to do the same thing here, we would be getting different numbers. So that's the reason we decided to use this library.
Okay. All right. So then hash underscore object, suppose I want to do so equal to hashleaf dot SHA-256 name dot encode. If what does this like SHA-256? What is it like?
SHA-256 is, let me just double check. It is a way of calculating hashes, I believe.
Oh, okay.
It is a bit beyond the scope of this course, but it's just a way of generating hashes. and then we get an object from that, and then we convert it to an integer using hex digest. You don't really need to know how to do this. I was able to do this just through searching online for different libraries. But yeah, this isn't something that you need to be able to replicate.
Even hash underscore object, which is what just we declared when we're printing it, hash object dot hex, hex digest. That I haven't declared hex digest. Where am I getting this from?
So this function call, so we import hashlib
Oh,
And-
okay.
call in this library. This returns a hash object. So this object has a method implemented called hex digest.
Oh, okay. It's
Uh,
there in the library.
Yeah, and then we convert that to an int from hex because this returns a hex value. We return it, convert to an int, and then we just modulo 3 plus 1 in order to get the question number.
Okay, okay. Okay, now I haven't seen the rest of them. I'll have to go through.
Okay.
So that's pretty much it. Thanks.
Okay. Okay, if there's no additional questions, I will hand it off to the learning support staff. And yeah, I hope to see everyone tomorrow. Hopefully my connection issues are resolved by then. And yeah, have a nice night, everyone. And I will make sure to assign host when I leave.